So finite element analysis, just to give you a quick overview here, it is a numerical approximation utilizing partial differential equations. So if you look at the top bar there, it's fixed on the left-hand side. We're applying a force, a downward force, on the right-hand side. And if you started dividing that bar up, you could cut it in half and then cut those two halves into quarters, and so on and so forth, down to basically an atomic level. What finite element analysis does is it takes that one continuous problem and divides it up into specific elements, or tetrahedral elements, which is what you see right below. And this method is called discretization. We're basically dividing it into discrete elements. From there, that's what allows the software to solve for displacement, for stress, for strain across these elements from the load to the fixture. So the case study that we're going to look at, or actually, sorry, some of the common design requirements across all industries is, number one, stress and displacements per the loading conditions. So if you look at that press at the bottom, how much stress develops when the load is applied? What is the displacement, that we're seeing out of this? Is it a quarter of an inch? Is it an eighth of an inch? Another design criteria would be factor of safety. A lot of times you have to meet or exceed a specific factor of safety of 2 or 3 just to make sure that your design is safe. Another thing that designers or engineers should be concerned with would be fatigue or life cycle. How long will the design last? Unless it's a one-time use kind of throwaway item, we need to make sure that that's going to last through a number of cycles. So 1 million cycles or 100,000 cycles. You can also look at fatigue on the opposite side and design your part to specifically fail at so many cycles. You have to sell another one at some point. And then optimization as well. And this is something that a lot of engineers address manually, but we can address this through the software automatically. How can we make the design lighter, stronger? How can we make it cost less? So that's something that we're going to address as well through the finite element. So the case study that we see here is going to be this press. And I'm going to be applying a 7,000-pound vertical load underneath. So for the static study, static is fixed, it's immovable, and it's at essentially one time step. But we need to make sure that our stress is below 14,000 psi on this press. Factor of safety needs to be 2 or higher, and the displacement has to be less than 0.0375. What you're going to see is after we run this study, the stress is actually going to come out to be right around 13,000 psi, so we're meeting that goal. We're going to meet the factor of safety goal of above 2 at 2.51, and our displacement will be less than the 0.0375. So let's switch into SOLIDWORKS and take a look at the press. Now everybody should be familiar with SOLIDWORKS at this point. One of the benefits of simulation is we are sticking with or staying right inside of SOLIDWORKS. There's no export to another program or anything like that. You're going to see at the very top that we add another Command Manager tab, so you're used to the assembly, the layout, the sketch. We now have simulation. We can add a study, so this is where we tell the software what type of study we're going to do. We're going to be looking at static, but I just wanted to kind of cover the rest of the studies that we can do. We can do frequency analysis, so if you're worried about natural frequency, stay away from a specific frequency, a rotating motor or something like that. We can do buckling, any thin, slender columns in a compressive load. Thermal loads as well. We also have a module for drop test. Fatigue, which we will be covering. And then we also cover ASME-specific pressure vessel design. And then the highest package of simulation, which is premium, covers nonlinear and linear dynamic type studies. We're going to stick with static for this run. Again, we're inside of SOLIDWORKS, so everybody should be used to the feature manager tree. When we start a new study, just like Excel, it starts a tab down here at the bottom and divides up our feature manager tree or divides up this window, so we have a study design tree. So very similar to SOLIDWORKS, we have our study design tree here. The parts themselves, what you're going to notice is plain carbon steel carried over from the material that was located inside of SOLIDWORKS. So as your designers, or as you are designing these parts, you're assigning materials. These materials are in the same database as SOLIDWORKS. So it's all one unit. The nice thing about this is if I do assign a material, anything in red for simulation carries over, and it says this is what is required for my specific type of study. So we've got green check marks is telling us we're good to go. We now have to tell the software, how is this realistically held down? So we're going to be assuming that the base of this press is fixed or, held to the floor or is immovable. Our loads can be forces, torques, pressures, gravity. We have a wide variety of loads. I'm going to be applying a force, and this is actually going to be a 7,000 pound force that I'm going to be adding. We get feedback in the tree that I did indeed, apply a 7,000 pound force here. Creating the mesh is the set or the part of the study where we discretize it or break it down into elements, and you see simulation does a very good job of having two cells across the minimum thickness. It does this because, again, we're inside of SOLIDWORKS, so it recognizes the geometry thickness. And this is usually a good rule of thumb for any finite element package to make sure that your results are valid. I can hide my fixtures and my load just so we can kind of clean this up a little bit. Now, the very first plot that we see is stress. What you're going to see is this deformation scale up at the top. It's 159 times the true deformation. The nice thing about this, though, is with it being exaggerated, we can really see, with the animation, how is that actually moving. So we get a good indicator of, okay, my load is applied properly, my base is fixed properly, it's working correctly. One thing with the scale over here, we see that it is in megapascals. I'm used to PSI. It's very easy to change that. It's through a main menu. And I can also change this to true scale. So this is the true deformation scale. And what we're seeing is my maximum load here is 12,753 PSI, or that 13,000 PSI. So we're below our requirement there. The next thing that we can look at is actually displacement. And scientific notation drives me nuts, so we can always switch to floating. And what we see is 0.018. We needed to say below 0.0375. So we're meeting that criteria as well. And again, this is an exaggerated scale. The next requirement that we wanted to stay within is the factor of safety. Now, your factor of safety is essentially your yield versus your actual stress, so the yield of the material. So as we go through, I want to see the factor of safety distribution across the whole model. And what we're going to see here is that my minimum factor of safety is 2.51. That's any areas that are in red. And if we look here, I can actually isolate that down to areas essentially above 3, or let's say 50. So we're isolating down areas above 50 factor of safety. We could actually reverse that. So this is everything below. So we see that we're meeting throughout the entire structure that 2.51 goal. We can do that same type of clipping as well for stress. So if I switch back to my stress plot, let's say, yes, 12,000 was our maximum, but we want to see everything above 5,000. So if we do that, we can see where the stress is being invoked at 5,000 and up. So this is a nice feature that we have. The other type of plot that I wanted to talk about is what we call a design insight plot. The design insight plot shows us how the load actually travels through the structure. So as I move this slider, we're essentially applying the load or allowing the structure to see how it is going from zero load to full load. So we can see areas of the structure that we could actually remove material from, which would be the thickness here, the spread in between our legs, as well as this back plate really isn't seeing a lot of the load. The nice thing about this plot is this is going to actually lend itself well to the optimization. We're going to utilize it to know where we can limit or change our dimensions. So we met all the criteria for our static study. I want to switch back to the PowerPoint and let's talk a little bit about the fatigue case study. So our fatigue goals, this press needs to run, let's say, 500,000 cycles, and we can see no more than 70% damage at 500,000 cycles. The results that we're going to get out of this is the minimum life is actually 800,000 cycles. So we're going to exceed that goal, and we're going to only see 63% damage in very small areas when we run this. So just like the static study, I'm going to actually start a fatigue study here. We have two options. We have variable amplitude and we have constant amplitude. We're going to stick with constant amplitude for this run. And then one of the benefits of being inside of SOLIDWORKS and inside a simulation is we actually link to other studies. So let me make sure that this is 500,000. So I'm linking to study 1 for my loading. So it's that 7,000 pound load. I need to apply my material. It's going to be plain carbon steel. Now one thing here that we do need to add for any fatigue analysis is something that is called a stress to number of cycles curve, or an SN curve. If you do not have it for the material, you can either get this from actual empirical testing, or if it is for a carbon steel or ferrous alloy, you can use a ASME curve or ASME derived curve, which I'm going to actually do here. So what we're going to see is, with that being derived, we can see that this is the stress per number of cycles. And for a ferrous alloy, in general, you're going to meet a criteria where below a certain stress, the part will actually last forever. So let's go ahead and apply that for our parts and run our fatigue study. Now the two results that we gain out of a fatigue study are damage and life. So if we look at our damage plot, and I adjust this to be floating again, we can see it's 62% damage, and those areas of damage are right at these fillets where we saw the high stress. So the results make sense here. It's kind of a sanity check. Our life plot, and again, if we look at this and I switch this to floating, so 795,000 cycles, so 800,000 cycles this is lasting through up to that percent damage. So we're meeting and exceeding that option or those requirements. So our design's looking pretty good so far. The next step is we want to make sure that we have an optimal part. So we want to run what is called an optimization study. So our optimization goals, one of them usually for almost any industry, is weight reduction. We want to reduce the weight of this component. It's less weight to ship to our end customer. It's less material, and in general, usually less machining. So weight reduction, the original weight of this is 163 pounds. We still need to make sure that our stress is below the 14,000 psi and that our displacement, again, stays under the 0375. So from that design insight plot, we had three dimensions that we can change. Essentially this height, which what you're going to see here is called the back height. I'm going to vary that from 2 to 4 inches. So we're going to tell the software we can adjust that parameter or that dimension. The back plate length as well, and this is going to go from 6 to 14.75. And then in between my feet, I want to open up that gap. And we're going to vary that from 4 to 9.75 inches. I'm also going to tell it the two parameters that we want to hold true. We have to be less than 14,000 psi and less than the 0.0375 displacement. What we're going to see is after this optimizes our optimization results, the new weight's going to be 142 pounds, which is about a 21 pound difference or reduction in weight. It's a savings of $7.40 per press. So if you figure you manufacture 200,000 of these a year, it's over almost $1.5 million worth of savings in raw material at 35 cents per pound for steel. So you can see where optimization really comes into play in saving your company money. So let's start an optimization study. So the very first thing that we have to add here is we have to tell the software what dimensions we're going to change. And if I double click on my screen and I actually want to show my dimension names, actually it doesn't matter with this one. So these dimensions are what I want to change. Now I already have these set up. So I have a back plate, my feet width, and my back height. Now I want to tell it that this is going to just be a range. So I want the software to tell me what is optimal. So for my back plate, we're going to go between 6 inches and 14 1/4. My feet width is going to be between 4 and 9.75. And again, this is linking to these dimensions. And my back height, which is this one here that's starting out at 3.937, I'm going to tell it can go between 2 and 4. Now we also have to tell the software, how can we constrain this, or what are we looking for? Well, our stress needs to stay less than 14,000 psi. And our displacement needs to be less than 0.375. Now these are actually linked to sensors in the model, and if we look at these sensors and I edit the sensor of stress, we're specifying simulation data for stress across the entire model. So we're picking up from the geometry and from the run with a sensor which is in basic SolidWorks, our constraints for this run. The last sensor is for mass, and what we want to do is we want to minimize that. So next step is simply to tell the software to run. It's going to process 15 different scenarios. And what you're going to see is on the screen as this runs, is it making adjustments to this geometry. So it's actually adjusting the size of it to come up with an optimal design. I've been in design scenarios before, or actually in industry, and I've tried to optimize things manually. And I've come up with what I thought was the best optimal design, ran the optimization inside of SolidWorks, or actually inside of simulation, and there were changes or options that I hadn't even thought of. So this software actually allows you to come up with really good options here for what we're seeing. So what you're going to see is anything that is in the gray means that it passed our displacement or our stress. And the stress option did not take. That's why it ran differently. Okay. So 14,000 psi. Let me rerun this here. I apologize. It took 0 instead of 14,000. So as we allow this to run, we should see several others that are actually going to fail here. And we want it to be less than 14,000. I apologize. So let's rerun here. We should receive good results. There we go. So anything that comes up in the red or pink color, that's actually failing, and it's failing due to the fact that the stress is too high. Anything that comes out in the gray, which you just saw with iteration 5, we're below that 14,000 psi. So we're seeing iteration 5 and iteration 7 are passing. Everything else is actually failing, and it's failing because of that highlighted cell, which is the stress. So without optimization, we could manually have to run these as separate studies to try to figure out essentially what is optimal. So as we see, we have several options: iteration 5, iteration 7, 9, and 11. If we select on any one of those, we can see how the geometry changes. So you can see that the feet width narrowed down here. If we go to optimal, what we're going to see is that the width of the legs is quite large. This back plate is shallower, and the back height actually went down just a little bit from 4 to 3.67. Now, I did tell it a range. I didn't tell it specific discrete values, which means staying to 1/8 of an inch or 1/4 of an inch. With that, what we can do is actually take and go back to our variable view, and we would specify with range or discrete values if we wanted to. At this point, what I would do is actually take the optimal design, adjust these numbers to be whole numbers, usually round up, rerun it as a static study. And by the way, if we switch to the static study, it keeps whatever iteration or size we specified that's highlighted in the design study. It keeps it here. So we can actually rerun that study at the new dimensions and just verify our stress is 13,978, so we're below the 14,000. Displacement is 0.022, which is less than the required. And factor of safety was one that I didn't have in the design study, but again, as a sanity check, we're above 2. We're at 2.29. So we can see that this is actually very powerful software, the optimization portion of this.